Contingent claims, state prices, risk-neutral probabilities. We're going to take a little deeper look at discount factors, our basic pricing ideas, and connect them to some other ideas that are very useful. So, states and complete markets. There's a lot of different words here, and we got to learn what these words and ideas mean. So let's start with states of nature. We've already thought about things that way, and there are states of nature. I'll use little s, 1, 2, up to capital S, to denote the possibilities of things that could happen. Simplest, looking at tomorrow, it could rain or it could shine. Two possibilities of what could happen. Of course, this is finance, so another classic example, we'll think of the states of nature, the things that could happen, as the different values of the S&P 500, and think about what happens if the S&P 500 goes up and goes down. Contingent claims, a very special kind of asset. It's a contingent claim, and it pays 1 unit in one state and nothing in any other state. And it has a contingent claims price, which I call PC for contingent claim. PC of S tells us the price in any state S. So for example, I drew a case here where there's 4 possible states. The contingent claim to state 2 pays 1 unit in state 2, nothing in any other state, and it has a price, contingent claims price, PC of 2. So thinking about it, typically a contingent claims price will be a number less than 1. You only get any money if one state occurs, and so the contingent claims price will be lower than, and it'll reflect the probability of that state happening. It'll typically be a smaller number. Not always, but typically. A complete market is a market structure where you can buy all possible contingent claims. If there's 4 states of nature, you can buy consumption delivered in each state of nature individually. Now that need not be directly traded. A complete market is also one where you can synthesize a contingent claim to every state of nature, and in that sense get anything that you could possibly want. An incomplete market is a market that doesn't have that many different securities traded, where not all contingent claims are available. So for example, we'll model a stock in many cases. In this binomial model, you put $1 in and you get U out, maybe $1.20, or D out, maybe 90 cents, depending on what happens. If that's the only asset available, you have an incomplete market. You have to buy this bundle. You can't get either U or D separately. You can't move your money into U or D or D. So sometimes you can create contingent claims from other underlying securities, and that's called spanning. If you can span contingent claims with other securities, then you can create them even if they don't exist. So here's an example. To continue our example, a bond would be you put in $1 and you get RF in each state. And a good numerical example is just if the interest rate is 0, you put in $1, you get out $1 in each state. Now, if you have both a bond and a stock, and you can take portfolios of the bond of the stock, then you can synthesize a contingent claim by long-short positions in the bond and the stock. And you're going to do that as one of your first problems, just to check that makes sense to you. Spanning can also happen not just by the number of securities equaling the number of states, and you can see obviously a sort of linear independence that you need, but you can have spanning by dynamic trading as well. So here's an example. Suppose that there are 2 steps, time 0, 1, and 2, and the investor can retrade at time 1. Then it turns out that if you have 2 securities, this stock and this bond, and you can retrade at time 1, then you can span all 4 states of nature, create 4 contingent claims out of 2 securities, and the opportunity to retrade them. So when we say complete markets in finance, that's often a shorthand. Obviously, markets are not complete because you can't buy claims on rain and sun tomorrow. But we'll often refer to a market as complete if all claims on, for example, the S&P 500 going up and down are traded, even though claims on rain aren't traded. So that's, in some sense, complete enough, and we use the complete word in that case. One of the biggest cases to keep in mind where this complete business comes up is in option pricing. So here, for this state will be the value of the S&P 500 at time capital T, and I've drawn a couple of assets here. We typically think here's on the x-axis is the value of the S&P 500 at capital T, and a bunch of different other payoffs can be given by the graphs of their value as a function of state. That's what we've done here too. Value is a function of state. So a stock, for example, the S&P 500 itself is just the 45-degree line. As the value goes up, the value of that payoff goes up. A bond pays off the same amount no matter what happens to the S&P 500. A call option pays off nothing until the strike price and then pays off linearly. And a contingent claim is a security that gives you a payoff, a unit payoff when and only when the S&P 500 hits a specific value. So a question is, can we get any shape of payoff? Can we get any function? And so here we have some classic spanning theorems. If you have all call and put options available, then you can synthesize any contingent claim. And of course, from any contingent claim, you can synthesize any function, any payoff you'd like. So all call and put options allow you to synthesize any contingent claim. Similarly, we have the Black-Scholes formula and that idea behind option pricing, where in that situation, dynamic trading of just a stock and a bond allows you not just 4 states of nature, but you can achieve all contingent claims and any function. So when we say complete markets, markets can be complete because contingent claims are traded. They're not in reality. Markets can be complete, at least complete on some security, if there's a sufficiently rich set of securities or a sufficiently rich set of trading opportunities.
Professor, does S have to be finite?
No, S does not have to be finite. As usual, I'm doing the simplest possible cases to get the ideas, but much more generality hides under us. So we can have a countably infinite number of S's. You can imagine the mathematics get more fun when you do that. You can have an uncountably infinite number of S's. You can have continuously distributed random variables. And not only that, but time doesn't have to be discrete. Time can become continuous as well. So I put up this option pricing example in part to motivate the answer to that question. Here, the states of nature are continuous. The S&P 500 can take any value it likes, at least in our mathematical treatment. In reality, it only goes to decimals. And then the functions here are continuous functions. The mathematics all gets hairier, but the ideas are well represented by a finite set.
Okay, thank you.
So we're going to stay with the assumptions that markets are complete for a while. That simplifies a lot of things, and then we'll go on later to incomplete markets. So assume that markets are complete. Let's think about pricing other securities. The price of any payoff, a payoff here is just a bunch of contingent claims. It specifies how much you get in each state of nature. So the price of any payoff is the sum of the contingent claims prices, what each payoff is worth, times the payoff in each state of nature. To make that look prettier, something like what we've seen before, why don't we just multiply and divide by probabilities and define M of S, define the discount factor as the contingent claims price divided by probabilities. Then we represent the prices of the payoffs by expected discounted payoff. There's our friend, the discount factor. Now, how much did we have to do? What ingredient did we need to do that? It's called the law of one price, the statement that the price of a bundle is equal to the a la carte menu, how much it costs if you buy each element as a contingent claim. That is an assumption, and it reflects a sort of an absence of arbitrage, a little bit of rationality by our investors. So let's think about what we've done. One of our big questions is, when can we represent prices by expected discounted payoffs? When does there exist a discount factor? We've just proved a theorem about when a discount factor exists. When can we represent a set of prices and payoffs by price equals expected discounted payoffs? In this case, the theorem goes, if the markets are complete, if the law of one price holds, then a discount factor exists. And in fact, we know how to construct the discount factor. You just take the contingent claims prices and divide by probabilities. That tells us something philosophical. It tells us that price equals expected discounted payoff is really fairly innocuous. And all the action in asset pricing has to come from tying the discount factor to other data, not just this bundling. When we do this with continuous states, not just discrete 1, 2, 3, 4, 5, this is especially important because when you integrate over states, you need some measure. So in fact, typically we don't use raw contingent claims prices. We multiply and divide by probabilities. And that's why we use the words state price density sometimes to refer to what I've called the discount factor. That's what it's doing here. It's just it's telling us the state prices in a way that we can integrate and then multiply by probabilities in order to find the value of something. Now, another way of representing the same ideas. We had price as a bundle of contingent claims. We had price as state price density or stochastic discount factor. Now I'm going to introduce risk-neutral probabilities, which express the same ideas in a different way. So let's define the risk-neutral probability as the contingent claims price divided by the sum of all contingent claims prices, or similarly with the discount factor, or most simply of all, just take the original probabilities and then weight them by the discount factor and the risk-free rate. What happens if you do that? Well, if you plug this definition into our pricing formulas, you'll find that now the price can be expressed as 1 over the risk-free rate times the sum of the risk-neutral probabilities times the payoff, or the expected payoff divided by the risk-free rate. But I use E star because we're not using real probabilities, we're using these transformed probabilities. And by the definition here, you can see, since it's contingent claims price divided by all contingent claims prices, that the risk-neutral probabilities have to be between 0 and 1, and they sum up to 1, so that they are, in fact, a genuine set of possible probabilities, even though they're not the real probabilities. That's a gorgeous formula. Risk-neutral pricing is very simple. And so by using these transformed probabilities, then we get to use a very simple pricing formula. Another way of saying it is that it's a change of measure, because what we've done is we've taken the original probabilities and then multiplied them by something that changes them into a new set of probabilities that makes life look very simple. It's very intuitive as well, and sort of deeply philosophical, if you'd like. Let me expand the M into the ratio of marginal utilities, and you can see what's happening is we take the original probabilities and then we give higher probability to high marginal utility states. So the risk-neutral probabilities, they overweight unpleasant states of nature where consumption is low and marginal utility is high. And that's a very intuitive way of thinking about risk aversion. People who are risk averse pay too much attention to very unpleasant states of nature. People who worry about planes crashing, planes don't crash that often. Well, if you worry about it a lot, you're showing your risk aversion, and maybe that's a rational thing to do. When do we use risk-neutral probabilities? Well, the formulas are really simple. So they're very useful when the risk premiums, when the actual probabilities don't matter that much. If you're pricing options by arbitrage, for example. So summary, in our complete market setting, we found 3 different ways of thinking about the discount factor and a deeper view of what the discount factor really is. Price equals expected discounted payoff. That's what that means in a state diagram. That's the same thing as just a bundle of contingent claims. And it's the same thing as risk-neutral pricing with these distorted set of probabilities. The stochastic discount factor is the same thing as a state price density. It's the same thing as a transformation to risk-neutral probabilities. So you've learned how to express the same idea in 3 different ways, 3 different very intuitive concepts, and you know how to transform from one to the other. Given a discount factor, you can find contingent claims, you can find risk-neutral probabilities, and express the problem you have whichever way makes the most sense to you.
So is the state price density over here unique?
Yeah, naturally, I showed existence, and naturally the next question is uniqueness. In a complete market, the answer is yes. Why? Because there's only one set of contingent claims prices. You can't have multiple prices for the same thing, otherwise you and I could make a whole lot of money. So there is a unique, it's just the contingent claims price that they are. And then of course the transformations are each unique. So we're just multiplying and dividing by things. So there's a unique set of risk-neutral probabilities, a unique stochastic discount factor, and a unique set of contingent claims prices when markets are complete. When markets are incomplete, we're about to have that fun, and that'll be different. So we're still thinking about complete markets. Let's go back and look at the investors in a complete market. What's the investor's problem? Well, here's our friend the utility function, max utility plus expected utility tomorrow. And I'm going to write his budget constraint now as today's consumption plus the discounted value of tomorrow's consumption equals initial wealth. Now let's look at that a little more carefully. What I mean by expected utility is the sum over states, probability of each state, times the utility of consumption in that state. The budget constraint, what do we mean? Why is that the budget constraint? Why does the discounted value of future consumption show up? Well, in a complete market, what the consumer does is goes out today and buys contingent claims to future consumption in every state tomorrow. So that he has to go out and buy contingent claim for rain, how much he wants to eat if it's rain, contingent rain for shine, how much he wants to eat if it shines, and so on and so forth. So the meaning of expected discounted consumption in a complete market is the contingent claim value, buying enough today, and then you just exercise those contingent claims tomorrow. Okay, with that stated as the consumer's objective and constraint, all you have to do now is take partial derivatives with respect to today's consumption and with consumption in each state in the future to find the first order conditions. And the first order conditions are just that the discount factor in each state, the probability, the contingent claims price divided by probability, is marginal utility in each state. So we often write that as MT plus 1 is beta U prime of CT plus 1 over U prime of CT, but watch out. When we say two random variables are equal, that means in each state they're equal, not just they're equal on average or something of the sort. We can also divide the things at time t plus 1. This expresses time t to time t plus 1 in a particular state. Rather than thinking about time t to time t plus 1 in a particular state, why don't we think about one state versus another at time t plus 1? And I've graphed that here. This is the underlying way we think now about investors choosing among risky possibilities. The price line that they face is the ratio of discount factors, or contingent claims prices divided by probabilities, and then the statement that marginal utility equals this marginal rate of substitution equals that price ratio just shows up like this. There's the price ratio, there's the indifference curve, there's marginal rate of substitution, there's the consumer's choice of consumption in state 1 versus consumption in state 2. There is our consumer taking on some risk, in this case a little less in state 1 and a little more in state 2, in response to price ratios. That's a fundamentally different view. This is what has happened to asset pricing. In the 1950s, we might have put utility of Google and Microsoft. Well, they didn't exist. It would have been GM and Ford, and thought about utility of different stocks. That's not how we think about It's not how we think about microeconomics and stocks. The first round of finance thought about means and variances as things investors cared about. There was utility for means and variances and the mean variance frontier and all that sort of thing. Now the cleanest treatment, that isn't wrong, it's a special case. The cleanest treatment that we'll follow is to put on the axis payoff in state 1, payoff in state 2, and then traditional apples and oranges microeconomics just applies perfectly and simply. That's a lot simpler than this, although really there's a lot more axes because there's many more states of nature. So what have we learned? That price equals expected discounted payoff. That statement really doesn't involve a lot of utility functions. That's just the bundling of contingent claims. Where utility functions come in is in how investors set marginal utility equal to the contingent claims price vector that they face. And in equilibrium, how that contingent claims price vector has to adjust. Second thing we've learned from looking at this, now quite typically investors have positive marginal utility. They always want a little bit more. That implies, if that's true, then we know they must face in equilibrium a market where the marginal rate of substitution, where the discount factor is positive in every state of nature. So that came up already. I claimed that the risk-neutral probabilities were always positive. How did I know that? Well, because original probabilities are always positive and because marginal utility is always positive. So looking at this tells us something else. It tells us that the discount factor is going to be a random variable that's always positive no matter what happens, so long as it's connected to marginal utility. So we're still thinking about complete markets, and a follow-on of our analysis of what investors do in complete markets lets us think about risk sharing. So here's the crucial observation. Each of us has different utility functions and different consumptions, possibly, but there's only one price. When we go buy apples, we each pay the same price, and when we go buy securities, we also pay the same price. That's the same for everyone. So let's think about that basic first order condition, and now let me use I to denote one person and J to denote another person. There's Mr. I's first order condition, and there's Mr. J's first order condition, and each of those is equated to the common price ratio, state by state. What does that mean? That means that marginal utility growth is the same for all investors. That's a very deep statement about risk sharing. And let's look at it in a little more detail with some special cases. Another way of showing what's going on here, we each face the same prices. The budget constraint is the same for each of us, but each of us may have different indifference curves. So that just means that our marginal rates of substitution are equated at each of our optimum, even though each of us may be eating different things. So what does that mean? Well, let's take a special case. Suppose that we all have the same discount factor and the same utility function. What happens then? Well, then the beta is the same for everybody, the gamma is the same for everybody, that marginal utility is the same for everybody because we're facing the same price ratio, and therefore consumption growth is the same for everybody, ex post. Not expected value, ex post consumption growth is the same for everybody. That means that complete markets give us perfect risk sharing. We all go up together or we all go down together. It doesn't mean we're all the same in levels. So here's what it might look like. JC is me, BG is Bill Gates. Bill Gates has a lot more than I do. But we should, if we lived in a complete market, we would share risks equally. In good times, we both go up. In bad times, we all go down. That's a beautiful feature of what asset markets do. One of the big functions of asset markets is they serve to help us share risks in this way. You can see that where risks are perfectly shared, where everybody's consumption is moving up and down, we're all sharing in the aggregate risk. And that feature of asset markets, the fact that they share risks as well as possible, that's why in our formulas we keep using aggregate shocks. We keep relating asset prices to aggregate consumption, to the market return, to big things, and not to things that happen to us individually. Because the markets, one reason is because the markets share out all of the individual specific shocks. Second thing, a more general version of this kind of analysis, you've seen intuitively that it's very pleasant that asset markets are serving a socially useful function by letting us share risks as well as possible and to let the people willing to write the insurance provide that insurance to the rest of us. A deeper way of saying that is that in a complete market, that the allocations delivered by financial markets are Pareto optimal. A benevolent social planner who knew everything couldn't do any better. Finally, there is a theory of aggregation that flows out of this. We often use aggregate consumption. We put utility of not each individual's consumption, but the consumption, the total consumption of everyone in the U.S. economy. Well, since in this very simple case, everybody's consumption is the same, you can see it's the same as the average, and you haven't done much damage by that. There's a deeper theory of aggregation that allows you to use the utility of average consumption instead of the sum of each individual's utility function. And an easy version of that also flows out of complete markets analysis. So next, I'd like to introduce a geometric representation of the same ideas that I find very convenient for keeping things straight. We're thinking about states 1 to S, so the listing of all the things that the discount factor could be in each state, or the listing of all the values that the payoff could be in each state. We can think of those random variables as vectors in RS. And more generally, we think about random variables as vectors in a function space like L2. Now, when we think of random variables as vectors in this way, it's very useful to think about spatial relationships between them. And I want to give you an analogy that if you're familiar with it, will make this all go down much easier. Think about a regression. In a regression, we run a regression of y on x with an error term. And in particular, think of two different x's, x1 and x2, with an error term. And we use all sorts of geometric language to describe that. We call x times b the projection of y on x. We call minimizing the size of the error, we call the error the size, and we call minimizing the size of the error the thing that the regression tries to do. When we notice that the errors there's no second moment between the errors and the right-hand variable, we say the error is orthogonal to the right-hand variable. Orthogonal meaning at right angles. Where does that geometric language come from? Well, a common way to do that is to plot the x's, the things that can happen to the right-hand variable. I put them here as 2 points. This is a three-dimensional diagram with the third dimension going into the board. So x1 and x2 are like 2 points on a three-dimensional diagram. Then there's a plane of possible values where b1x1 plus b2x2 can go. The plane of random variables that are spanned by x1 and x2. So I've drawn that. If x1 and x2 are like this, that's a plane going a little bit in the board. Y is a random variable off the plane. So the way we think of a regression is is finding the point on the plane that is closest to y, minimizes the size of the error, thinking of the second moment of the error as its size. And when we say projection, well, that really is we're projecting y on the plane, and the error orthogonal to the right-hand variables means that this error vector is in fact at right angles to the plane. That's a very useful language. Let's apply the same kind of language to what we're doing. We have a discount factor. Let us plot state 1 and state 2. This one is mercifully a two-dimensional diagram, but three-dimensional versions are coming. So let's think of state 1 and state 2. We have a discount factor. Well, that's a vector, and it's positive in all states, so it points into the positive orthant here. There's m pointing into the positive part. When we say e of x, now we can think of that as an inner product. We can think of that as m dot x, if you will, or that's another notation for inner product. And so, for example, if 0 equals e of mre, we can then say that the discount factor and excess returns are orthogonal because they are two vectors whose inner product is 0. So that lets us construct a state space representation, a picture of where everything goes. M is a vector in the positive orthant of our state space. An excess return is a vector like this. It's a vector at right angles to M. And the set of all excess returns, the set of all price 0 securities, has to be this set that is at right angles to M. Where's the risk-free rate? The risk-free rate, a risk-free payoff has 1, 1. The risk-free rate is a little bigger than 1, 1, but it's the same in both states of nature. Where are all asset returns? Well, asset returns are securities whose E of MR is 1, or the inner product of M with R is 1. How do you do an inner product? You take this vector and that vector, you project this vector onto that vector, and multiply the two together. So this is set in green is the set of all vectors whose inner product with M is 1. So all returns are vectors that lie on that plane. Similarly, where's all the price 2 objects? Well, all the price 2 objects are vectors whose inner product with M is 2, and therefore they all lie on that plane there. RF, of course, is the point on the price 1 where the two values are the same in both states of nature. So what have we got? You can see that the mapping from payoffs to prices is a linear function. We're looking at isoquants of that linear function from the state space to the real line, and you have a very pretty representation of where all of our objects lie. Excess returns, price 2 objects, objects of same price are on hyperplanes orthogonal to the discount factor. So let's summarize what we've learned about asset pricing in complete markets, when every possible contingent claim is either sold directly or you can synthesize it. First, when payoffs and prices are in a complete market, and if the law of one price holds, then we found that the price of any payoff is just the sum of its contingent claims prices. So there's a contingent claims price vector that represents prices that way. There's a discount factor such that price is the expected discounted payoff. And there's a set of risk-neutral probabilities such the price is the expected payoff divided by the risk-free rate, evaluated at those distorted risk-neutral probabilities. What have you learned? The contingent claims price vector, stochastic discount factor, and risk-neutral probabilities, you can transform from one to the other and use whichever representation is simpler for the problem at hand. The risk-neutral probabilities were very beautiful. They represent risk aversion as a probability distortion. And when you start thinking about psychology and how people answer surveys, people often pay too much attention to hurtful events. That's exactly what risk aversion says they ought to do. Another formula we looked at, the discount factor, is the ratio of transformed to original probabilities. So the discount factor is the same thing as the change of measure from transformed to original probabilities. We then found that our original prices discounted payoff, it just represents assets as a bundle of claims. It wasn't particularly deep after all. However, linking the discount factor or the contingent claims price or the risk-neutral probability to data, that's where we're going to get some bite if we want to test our asset pricing theories. The positivity of margin utility told us the discount factors needed to be positive in all states of nature, no matter what happens tomorrow. Positive discount factors is something that's going to come back, and we're going to think about that a lot more in the future. And finally, we learned something about the geometry of our asset pricing world. We can put things in this state space diagram where the discount factor then generates hyperplanes of different prices. And then we can look at all of our different zoo of asset pricing objects in that diagram and keep track of them. So we've talked a lot about discount factors and contingent claims when markets are complete. What about when markets are incomplete? That is, of course, the world we live in, so it's worth talking about. So here's our question. You see some prices and payoffs, and the markets are incomplete. Is there a discount factor such that the prices can be represented as expected discounted payoff? How do you construct such a discount factor? In the end, we're not here for philosophy, we're here for construction. And being able to construct a discount factor to represent prices is, of course, a very useful thing to be able to do. We're going to build up to two theorems about the existence of the discount factor. First one is based on the law of one price. And if the law of one price holds, then there is a unique payoff, X star, that can act as a discount factor. Second one, if there's no arbitrage, a different condition, then we'll find there's a strictly positive discount factor. The law of one price and no arbitrage are a lot weaker than a utility function, but they are basic assumptions about what investors do and how they behave. Okay, let's do the first theorem. The law of one price and how it implies that there exists a discount factor X star. You got to meet the players and the assumptions. The payoff space, which I'll call X with an underscore, is incomplete. We have to talk about since it's incomplete, we have to talk about the kinds of payoffs that investors can get. Incomplete means it's no longer the full RS when there's S states of nature. It means it's some subset of RS. So, two examples. Here is when there are two states of nature. Suppose there's only a single payoff X, nothing else is traded, then the payoff space is, well, you can buy more or less of that thing, but you can't buy anything else. You can't get your way here. So that's a market that is incomplete because that's the payoff space. Another example in 3 dimensions. So now we have up, down, and into the board as our 3 dimensions. There are 2 payoffs, x1 and x2, 2 vectors out there. The payoff space is all portfolios of x1 and x2. You can move around on the plane, but you can't get off the plane, so the market is incomplete. The payoff space, again, payoffs are not returns. Payoffs can have prices of 2, 0, or anything else. Don't confuse payoffs and returns. Okay, there's a payoff space which is limited. We're going to make 2 assumptions about that payoff space. First, that investors can make any portfolio. In other words, if x1 and x2 are traded, then the investors can also access any portfolio of x1 and x2, including short positions. That's why I've drawn the payoff space as the hyperplanes here extending from x1 and x2, not x1 and x2 themselves. That's an important assumption, and it's totally false in reality. I'm saying there's no short sale constraints, there's no bid-ask spreads, there's no transactions costs. Of course, you can generalize to all of those things. There are versions of the theory that does all those things, but that's not the assumption we're going to start with. We're going to start with perfect trading. Second assumption, the law of one price, or the linearity of the pricing function. That just says that if we can take a portfolio of 2 payoffs, AX1 plus AX2, the price of the portfolio is the sum of the prices of the individual elements. The daily special is the same as on the a la carte menu. That's a mild sort of rationality. Almost, we use the word arbitrage for something else, but you can tell if the a la carte menu was different from the daily specials, and you could sell back to the restaurant as well as buy from them, you'd make a fortune. Prices and payoffs like that wouldn't last very long. Those are our 2 basic assumptions. Now, to our theorem. The theorem is that if those assumptions hold, then, read slowly, there is a unique discount factor X star in the payoff space such that the price of any payoff is expected discounted by X star payoff for any payoff X in that payoff space. That's a theorem about the existence of a discount factor. Why is that a true theorem? Well, I'll offer you 2 arguments. First, geometry. Our assumption, the law of one price, says that the pricing function is linear. We've seen what a linear pricing function looks like. The price hyperplanes have to move out like that. Well, geometrically, if you have a linear function, any linear function like that can be represented by there's some X star, there's X star, and all these prices are generated as inner products with X star that's constructed to be orthogonal to the price hyperplanes. Right? Any vector on P1 here has the same inner product with x star and therefore generates the same price. An algebraic argument is easy when we have finite states. So let me give you that. Now first, let's think about a case where there's a vector of payoffs. There's n different securities. Now watch it. There's two kinds of vectors here. Each one of these securities is a payoff with a random variable. So each element here is a random variable, or you can think of it as a vector in Rs, but there's n of them. So there's n securities. The vector x is in Rn. It is a vector of random variables. Don't confuse n and s. If we have that set of securities, then the payoff space is all linear combinations of those securities where the weights are in Rn. So you can weight the securities different amounts. Now what we want to know is there a payoff of that form that acts as a discount factor? I'm just going to pull it out of my hat, though if you take 5 minutes you can figure out what it is from first principles. There it is. P prime e of x prime inverse times x. Let's just check that that thing pulled out of a hat works the way it's supposed to work. Is that in the payoff space? Well, P prime e of x prime inverse, that's a set of weights that's known ahead of time. So that is a set of portfolio weights times the original payoff. That is a weighted sum of the original payoffs. That is an available payoff. Check one. That's the easy part. The hard part, let's check that it does what it's supposed to do. That x star, if I take that x star and multiply it by any of the payoffs, or all of them, do I get the prices back? Well, just plug in. X star, let's just plug in, is P e of x prime inverse times x, and then we multiply by the x. Now take expectations, and voila, e of x prime cancels e of x prime inverse, and we're left with the prices. It works by construction. It was constructed to work. Fine, it works. That one may seem a little bit artificial. Let's take a more common example. If we start with a set of returns, a set of price 1 securities, this will make it a little more concrete. The x star, the payoff, is a vector of 1s, the second moment matrix of returns times the vector of returns. This is related to, this will look to you a little bit like mean variance efficient formulas, and there's a close relationship which we'll come to later. Now, this is almost a proof. What about when S is infinite? That takes a little bit more mathematics. It's called the Rietz representation theorem, and it basically states in infinite dimensional spaces that exactly this is true. In an infinite dimensional space, there is still always an element of that space which can generate a linear functional. So it's just that, but with infinite dimensions. So let's look a little more closely at our first existence theorem. The theorem that says that the law of one price implies a unique discount factor in X that prices all the payoffs. What does that say really, and what does it not say? Be careful. First of all, it says there is a unique X star in X. That doesn't mean that there aren't other discount factors that won't be in the payoff space. For example, let's look at this algebraically. If price equals E of mx, then we can always say E of m plus epsilon x, add some noise. If that noise is uncorrelated with the payoffs, then you get the same price. You get the same price out of a new discount factor formed as the old discount factor plus noise. So there will be many discount factors, and X star isn't the only one of them. X star is the unique one in X. Here's a diagrammatic version of the same thing in our state space diagram. I've taken an example where there's a unique payoff, a single payoff. That generates a line for our payoff space. X star will be a payoff in the payoff space. There it is. But there could be other discount factors. Here's a discount factor m. That generates the same price for all of our payoffs in the payoff space. E of mx, the inner product of m with x, is the same as the inner product of x star with x because the difference, epsilon, is off at right angles. That expresses the same thing in graphs as that expresses in algebra. So there's lots and lots of possible m's. In fact, there's a whole space of possible m's. Anything on that orthogonal hyperplane there can be a discount factor. All possible discount factors, in fact, can be formed this way. Any discount factor, such that the price, this is just defines a discount factor. The price is the expected discounted payoff. any discount factor m is of the form m is x star plus some additional noise, where that noise is orthogonal to the payoff space X. Why are there so many discount factors, you say? Because we have an incomplete market. If we had a complete market, the discount factor contingent claims price would be unique. But now it's not unique. There's only one in X, but there's lots of them that are not in X. Another way of stating the same thing, X star is a very special discount factor because take an arbitrary discount factor like M. Well, X star is the projection of the arbitrary discount factor onto the payoff space. That's a lovely little result and maybe an advertisement for thinking geometrically. If you did that with algebra, you'd never know how anybody thought it up. But if you just make the diagram, it's clear that any discount factor projected on the payoff space gives us X star. For example, a discount factor, your marginal utility of consumption growth might be out here, but your marginal utility of consumption growth and my marginal utility of consumption growth, which might be out there, they're not equal anymore because we don't have perfect markets, but their projections on the payoff space are the same. That's the sense in which with incomplete markets, there's some risk sharing, but not complete risk sharing. So now to our second theorem about discount factors when markets are incomplete. Positive discount factors and the absence of arbitrage. So I mentioned there's two theorems we're chasing. The first one is that the law of one price implies a unique discount factor in the payoff space. Our second theorem is that no arbitrage implies a strictly positive discount factor. Let's go see what that means and how it works. So here's the theorem. If there are no arbitrage opportunities as well as the law of one price, then there is a strictly positive discount factor. And strictly positive, again, means in all states of nature. No matter what happens, this thing comes out positive. Well, to talk about this, I have to tell you what an arbitrage opportunity means. And here's the definition. An arbitrage, there's no arbitrage opportunities if every payoff that is positive, non-negative, positive with positive probability. So you know you're not going to lose money. You might make some money. That payoff must have a positive price. So the definition of arbitrage in payoff language, here are the payoffs that are positive. This one's positive in both states of nature. This one's positive in state of nature S1, but 0 in state of nature S2. That one's 0 in both states of nature, so that's excluded. But everybody in here has to have a positive price. Why is that? Well, again, that's a modicum of rationality. Something that might be worth something can never lose you money. That has to have a positive price. A lottery ticket might be worth something. You're never going to lose money if somebody just gives it to you. That thing must have a positive price. That's the definition of arbitrage. Now, be careful. In finance, when we say arbitrage, we mean this. Colloquially, arbitrage means violations of the law of one price, making money for absolute sure, the same amount no matter what happens. We call that the law of one price. On Wall Street, they call arbitrage taking crazy bets. There's actually things called departments of risk arbitrage, which is an oxymoron. I don't want to make fun of them. Just be careful when you talk to people that the language means different things. In finance, that's what arbitrage means. Okay, now this theorem. What's the connection between arbitrage opportunities and positive discount factors? Let me explain the idea intuitively. Let's go the opposite directions, the easy one. Suppose that the discount factor is always positive, and suppose we have payoffs that are always positive. Well, the price of those payoffs is a sum of positive probabilities, positive discount factors, and positive payoffs. It's got to be greater than 0. In order to get a price less than 0 out of this, we would need a discount factor less than 0. That's not happening, right? If we rule out negative prices, we have positive discount factors. So that gives you the connection between positive discount factors, positive contingent claims prices, and the absence of arbitrage. In complete markets, the other direction of the theorem is easy as well. In complete markets, there's a unique discount factor. Now, suppose that discount factor was negative for some states of nature. Let's just look at contingent claims for those states of nature. Let's look at the sum of those payoffs in those states of nature. Those payoffs in those states of nature would have a price that's negative since the payoffs are negative. The real proof, I'm going to defer to the book because it takes a while and it uses techniques that aren't particularly useful anywhere else. But the theorem is true, and the important part is to remember the intuition. So now let's look at what this theorem says and does not say. And what's the difference between our no arbitrage theorem and our law of one price theorem? The no arbitrage theorem says if there are no arbitrage opportunities, there exists a positive discount factor. It did not say that that is a unique discount factor, and it did not say that that discount factor is in the payoff space. So these are very different characters of discount factors. Here is an example to try and make clear that distinction. Here is a payoff space, X, and I drew it this way. This payoff space, it always one thing gains and the other thing loses. For example, excess returns have a payoff space that looks like that. You can't make money for sure. Well, what happens in this payoff space? The X star is in that payoff space. There's the unique payoff that starts the payoff space. There's the payoff space. There's the unique X star. There's our law of one price guy. But our law of one price discount factor, that's negative in some states of nature. How do we form a positive one? Well, use our ability to create lots of different discount factors. Here are discount factors that are positive that price all the payoffs in the payoff space X the same as X star. So there is the positive discount factor. It's not the same as X star. And there are multiple positive discount factors, and the positive discount factors aren't in the payoff space. The theorems just say what they say. You just have to read them carefully to see what they do and don't say. This theorem is used in the following context. It's actually practical, not just philosophical. Suppose you had a payoff here. You're working for an investment bank, and they say, here's the space of payoffs we know how to hedge. A client wants to buy that one. What price shall we charge the client? Well, you don't really know what price to charge the client, but you don't want to quote a price that allows arbitrage opportunities, because your clients are really smart, and they'll game you if you do that. So if you choose one of these discount factors up here, that's consistent with these prices, and you know there's no way you can assign a price for that payoff that doesn't generate arbitrage opportunities and at least get something vaguely reasonable for what price you should charge the client. So our last topic today, formulas for X star. We had this lovely theorem. There's a unique X star in the payoff space that acts as a discount factor. Constructing that X star is going to be a useful thing to do in lots of circumstances. We had two formulas already. X star is the price times the second moment matrix of payoffs. In the case of returns, 1 E of RR prime R. But second moment matrices of returns are kind of ungainly. Let me show you a couple of versions that are much more useful in practice. So again, notation. We're going to think about n different assets. So X refers to an n-dimensional vector. Each one of those guys is a random variable. P is an n-dimensional vector as well. R is an n-dimensional vector of random variables, each one of which you can think of as a vector, and same for 1. Here's a nicer formula than 1 prime E of RR prime R. What's the difference in this formula? I used a covariance matrix instead of a second moment matrix, which is something much more common to use. R is the random variable here. Everything else here is known ahead of time. That's just another formula plopped out of my hat. You can derive it if you feel like it, but let's instead check that it works. If I use that X star and multiply by a return, what do I get? First term, E of X star R, that term is just 1 over F times the expected return, so E of R prime over RF. Next term, when I multiply this guy by R, what do I get? Everything out in front here is a constant, not a random variable. That's the random variable. So that's where E of R minus ER times R prime is. But wait a minute, that's our covariance matrix sigma. That sigma multiplies that sigma and gets rid of it, sigma times sigma inverse. And now the RF terms, the E of R terms vanish, and we're left with just RF over RF, or 1. So yes, 1 equals E of X star R prime, like it's supposed to. Next, how about excess returns? We use excess returns all the time. Excess returns focus us on risk premiums. If we try to use this formula for excess returns, it seems like we're in deep trouble. The price is 0, so we get 0 E of what? 0? Yes, indeed, 0 is the right answer. Theorems are very literal. They tell you exactly what you asked them, and they're not very smart about it. We asked for the payoff in the payoff space that generates prices. Well, that's the set of excess returns. 0 is an available payoff. You give nothing, you get nothing. And 0 is a payoff that generates all the prices. E of 0 times any payoff is 0. Thank you, I generated the prices. But it's a terrible one to use, because if we use x star equals 0, then the implied risk-free rate, E of x star is 0, the implied risk-free rate, 1 over x star, is infinity. We're representing asset prices with an infinite risk-free rate? That's kind of nuts. What can we do? It's the right answer. Let's ask a slightly different question. Why don't we make up a risk-free rate and use a discount factor that prices these payoffs plus our made-up risk-free rate? That's a better idea. And here's the solution. For any made-up risk-free rate, let's use x star and just use something reasonable. 1. There's a good risk-free rate. Let's use our same formula. X star is 1 over RF. And then I'm just using the formula here, expected excess return covariance matrix times the excess returns. Check for yourself, these ones are easy, that construction does what it's supposed to do. E of x star is equal to 1 over the assumed risk-free rate. And then E of x star times all the other ones equals 0. So that's a discount factor that works for the risk-free rate, that works for the excess returns, and is much more sensible than a shadow risk-free rate of 0. Now let's do continuous time, because of course lots of asset pricing goes in continuous time. How does all of this look in continuous time? So let's set up a simple continuous time environment, a n-dimensional vector of returns that follow mu dt plus sigma dz. Here I've just drawn the sizes of the matrices for you. N dimensions of returns, not excess returns, an n-dimensional mean, and then sigma is a n by n matrix multiplying an n-dimensional vector of Brownian shocks. So the covariance matrix, which is the same as second moment matrix in this case, is just sigma sigma prime, which I denote by the capital sigma. So that's the standard setup for a continuous time set of returns. What's the equivalent of x star? Well, we're looking for a discount factor in the set of returns that's a portfolio of the returns that also generates prices. And here it is. Again, you can derive this. Look for something of the right form. Derive the coefficients that work. I'm just going to plop it out of a hat and show you that it works. d lambda over lambda is minus RF dt, and then expected excess return, sigma inverse times the shocks. That shouldn't be too surprising. That's exactly the form that we had here. X star is RF, and then expected return, sigma inverse times the shocks. d lambda over lambda is RF, expected excess return, sigma inverse times the shocks. So it's the natural translation of the same ideas into continuous time. So does it work? Let's just check. Check that the expected value of d lambda over lambda is minus RF dt. That's the basic pricing equation for a risk-free rate. Check, it works. Second one to check is the expected return on any asset equal to RF dt times the covariance of that return with d lambda over lambda. I will leave it to you to plug d lambda over lambda into there, verify that the sigmas cancel again, the RFs cancel again, and we're back to exactly what we're supposed to be back to. So it's the same formula. This formula here has exactly the same spirit as this formula in discrete time. In continuous time, it's even prettier because that's a geometric Brownian motion, and d lambda over lambda is always positive. So in continuous time, we have this beautiful result that the unique discount factor that's in the payoff space is also always a positive discount factor, and therefore can be used to price derivatives and other contingent claims without worrying about arbitrage opportunities.